Okay, so here's something that will quietly ruin your confidence in human civilization. We have sequenced the human genome. We have photographed a black hole. We landed a rover on Mars and it sends us selfies. We built a vaccine in 11 months. We have an app that will tell you the name of a bird from 40 feet away just from a blurry photo you took while slightly drunk at a park. And we cannot tell you why you yawn. Not fully, not in a way that actually holds up. We have guesses, we have theories, we have researchers who have spent actual years of their one precious life studying yawning. And the current scientific consensus is basically, we think it might be a cooling mechanism? Maybe? Don't hold us to that. That's the thing nobody tells you about science. The story we get in school, and in documentaries, and in the kind of Instagram infographics that get shared by people who want to seem smart, is a story of relentless progress. Every year we know more. Every decade we close in on the answers. Every generation inherits a slightly more complete picture of reality. And that's true. Mostly. But hiding inside that story is a category of questions so ordinary, so basic, so embarrassingly close to things you encounter every Tuesday that it would genuinely shock you to find out they don't have answers. Not, we haven't finished the math answers. Not, the data is complicated answers. Flat out, nobody knows. Scientists have been arguing about this for literally centuries answered. These aren't questions about the nature of dark matter or the origin of consciousness or whatever the universe was doing before it started. Those feel hard. You expect those to be unsolved. The questions I'm talking about are things like, why do you need to sleep? Why does a placebo work? How does anesthesia make you unconscious? What makes something funny? Questions that feel like they should have been answered in 1987 at the latest. And the reason this matters, the reason it's worth actually sitting with, isn't just that the gaps are surprising. It's what the gaps tell you about how science works, and why being at the edge of knowledge feels so different from being in the middle of it. Let's start with sleep, because it is the most spectacular example of a thing we all do every single night, that we will do roughly a third of our entire lives, and that science has been genuinely baffled by for as long as science has existed. Here's what we know. You need sleep, desperately. Go without it for long enough, and your body starts failing in ways that are creative and terrible. Your immune system collapses. Your memory goes first, then your judgment, then eventually your grip on basic reality. There are documented cases of a genetic prion disorder called fatal familial insomnia, where people lose the ability to sleep and, over the course of roughly a year, die. Not metaphorically, die from not sleeping. So the body clearly treats sleep as non-negotiable. Whatever is happening during those hours is important enough that missing them kills you. The question is, what is it? And the honest answer in 2024 is that we are not sure. We have pieces. We know sleep is doing memory consolidation. Your brain is taking the experiences of the day and sorting them, flagging some as important, letting others go. We know the glymphatic system, a kind of waste clearance network in the brain, is dramatically more active during sleep, flushing out metabolic byproducts that have been linked to Alzheimer's. We know deep sleep is doing something essential with immune function. We know REM sleep is involved with emotional processing in a way that's still being mapped. But here's the thing. None of those explanations fully accounts for why you have to be unconscious for any of it. Memory consolidation. Why can't you do that while you're awake? Waste clearance. Why does that require turning your entire consciousness off? The brain is active during sleep. In some ways, more active than when you're awake. So rest isn't quite the right word. The leading theory for why sleep exists as a specific, vulnerable, unconscious state is honestly just because at some point in evolutionary history, it was too costly to stay awake for so many hours, and the body found a compromise, which is less a theory and more a shrug wearing a lab coat. You spend 8 hours a night, ideally, if you're not doom scrolling until 1 a.m., in a state that science can describe in extraordinary detail and explain only partially. Every time someone figures out one function of sleep, it turns out there are 3 more they hadn't accounted for. It's like trying to understand what a city does by studying one neighborhood, and sleep is almost the easy one. Anesthesia is where it gets genuinely uncomfortable. Every year, hundreds of millions of people go under general anesthesia. They are conscious. They receive drugs. They become unconscious. Surgeons do things to their bodies that would be agony if they were awake. They wake up with no memory of it. The whole thing works reliably enough that it's treated as a routine medical procedure. Nobody is entirely sure how it works. I want to be careful here because "we don't know how anesthesia works" is one of those claims that sounds like it came from a conspiracy forum, and it didn't. This is mainstream anesthesiology. The people who administer anesthesia every day will tell you this. The drugs clearly do something. They interact with receptors in the brain, they suppress neural activity in ways we can measure. But the actual mechanism by which they produce unconsciousness, the path from "this molecule hits this receptor" to "you are no longer experiencing anything," that chain is not complete. Part of the problem is that consciousness itself is not fully understood, which means figuring out how to switch it off is complicated by the fact that we're not entirely sure what it is or where it lives. This sounds like a philosophy problem, but it's also a biology problem, and an engineering problem, and a problem that becomes quite urgent when you're the person being cut open. What's quietly wild about this is that anesthesia was first successfully used in 1846. It's been in routine medical use for close to 2 centuries. It has been studied by some of the best minds in neuroscience and pharmacology, and the honest entry in a current medical textbook on the mechanism of general anesthesia reads something like, "not fully understood," in a textbook written last decade for doctors. This isn't a failure of science. It's what the actual frontier of science looks like. Technologies that work before we understand them fully. Practical knowledge outrunning theoretical knowledge. The map and the territory persistently slightly out of sync. Which brings us to a question that feels even more basic, more embarrassingly basic. Why does medicine work differently for different people? Specifically, why do placebos work at all? You probably know what a placebo is. You get a sugar pill, you think it's real medicine, you feel better. Haha, funny brain. That's the version most people have in their heads. But the actual research on placebos is so much stranger than that. Placebos don't just make you feel better. They produce measurable physiological changes. Your body releases real endorphins. Your dopamine pathways activate. In some studies, placebo treatments show clinical effects on things like Parkinson's disease. Not just "I feel less pain," but measurable motor improvement. There are studies where telling patients they're receiving a placebo doesn't eliminate the effect. Open-label placebos, where the researcher says explicitly, "this is an inert pill with no medicine in it, but we'd like you to take it," still work on a meaningful percentage of people. Your brain, upon being told it's about to receive treatment, starts doing something physiologically real, even when you consciously know the treatment isn't real. Nobody fully understands this. We have theories. Expectation plays a role. The anticipation of relief seems to trigger some of the same neural pathways that actual relief would trigger. Conditioning plays a role. If you've taken real medicine in the past, your body may have learned to associate the ritual of taking a pill with the feeling of getting better, and now replays that response automatically. But neither of those explanations is complete, and neither explains the open-label effect, which is the one that should, by all rights, just not work. What's unsettling about the placebo effect, if you sit with it for a second, is what it implies about the line between mind and body. If your brain can produce real physiological changes based on nothing but expectation, then the category of "this is psychological" and "this is physical" is blurrier than medicine has historically treated it. There's a whole field grappling with this called psychoneuroimmunology, which is a word that exists because the old categories stopped working. And if the brain can do that, if it can partially heal you by believing it's being healed, then there's something about human physiology that is still genuinely mysterious in a way that modern medicine, which is quite good at many things, hasn't fully cracked. Okay, different gear, same weird energy. Let's talk about bicycles. Specifically, how does a bicycle stay upright while you're riding it? Your first instinct is probably gyroscopic force. The spinning wheels create angular momentum that resists tipping. That's a real effect, but it turns out it's not the main explanation. Researchers built a bicycle with counter-rotating wheels specifically designed to cancel out gyroscopic effects. The bike's still balanced, so it's not that. Then you think, it's the geometry. The angle of the fork, the offset between the contact point of the front wheel and the steering axis. There's a thing called trail in bicycle design, and it creates a self-correcting steering effect. That's also real. But researchers have also built bikes without this geometry. They stayed upright. So it's not quite that either. There's a 2011 paper in Science, not exactly a low-bar journal, that explored this and basically concluded that bicycle stability involves a combination of factors, including the distribution of mass, the geometry, gyroscopic effects, and possibly things we haven't fully modeled. a thing humans have been riding for 200 years, in a paper published in 2011, still not completely explained. This one is my favorite because it's so visually stupid. You can ride a bike. Your 12-year-old self figured it out in an afternoon. The physics of how you're doing that in a stable, repeatable way apparently requires a science paper and an acknowledgement that further research is needed. There's a pattern starting to form here. The questions that turn out to be hardest aren't always the ones that feel hard. They're often the ones that feel so obvious, so built into the fabric of daily life, that nobody thought to ask them rigorously until someone had the nerve to sit down and try to write out the complete explanation, and found they couldn't. Yawning, sleep, anesthesia, placebos, bicycles. Here's one more. Why does scratching an itch feel so good, and why does scratching sometimes make the itch worse? Itch is actually a whole frontier in neuroscience. For most of medical history, itch was treated as a kind of low-grade pain, a signaling system that uses the same pathways. Then, in 1997, a researcher named Zhou-Feng Chen identified a dedicated itch circuit in the spinal cord, specific neurons whose entire job is itch. It's not just diluted pain, it's its own thing, with its own wiring. The satisfaction of scratching seems to involve a combination of the physical disruption of the itch signal and a pleasure response that's separate from just relieving the sensation. Your brain releases serotonin when you scratch, which, here's the part that gets interesting, can actually reactivate itch neurons, which is why you sometimes can't stop scratching and make yourself a little insane on a Sunday when you're trying to sleep and there's a phantom itch on your leg that keeps moving. But why the dedicated circuit? Why does the body have an entire neural system just for this experience, separate from pain? What was the evolutionary pressure that created a sensation compelling enough to require its own wiring? Probably something about parasites. Probably. That's the best guess. A nervous system that aggressively communicated, "There is something on you, handle it," may have been a survival advantage in environments full of insects and bacteria and things that embed in skin. But the full story of itch, why certain things trigger it, why it spreads, why some people are more sensitive to it than others, why certain mental states amplify it, is still being written. And this is the thing I keep coming back to when I think about all of these examples together. The gap isn't in the exotic corners of science. The gap is in the ordinary. The stuff your body does while you're commuting, or lying in bed, or sitting in a waiting room at the doctor's. The normal experience of being a person in a body is full of processes that science can describe, measure, and even manipulate, and still can't fully explain. There's a reason for this that's worth actually understanding, because it reframes what unsolved means. Science is not a single thing. It's a collection of different tools: observation, measurement, modeling, experimentation, applied to different problems at different scales. And those tools have not been applied equally to every question. Some questions got centuries of intense funding and focus because answering them had obvious practical value. The physics of motion, the chemistry of materials, the genetics of disease. Those questions got resources, and they got solved, or at least solved enough to be useful. Other questions, why you yawn, how anesthesia works, what makes something funny, either seemed too trivial to study seriously or were too complex to break down into the kind of clean experiment that produces clear answers, or were just sitting at the intersection of biology and psychology and physics in a way that didn't fit neatly inside any one department's budget. Humor is actually a great example of this. What makes something funny is a question that has been seriously studied. There are whole journals on humor research, researchers who study joke structure and comic timing and the neuroscience of laughter. And the honest conclusion is that we have partial theories. Incongruity theory says humor arises from an unexpected resolution to a setup. Your brain builds a prediction. The punchline violates it, and if the violation is the right kind of violation, you laugh. Benign violation theory adds a qualifier. The violation has to feel simultaneously wrong and okay, which is why jokes about things that feel too real or too cruel stop being funny and just start being uncomfortable. But neither of those theories can tell you why something is funny to one person and not another, why the timing of a joke matters as much as the content, why the same sentence is hilarious in one context and completely flat in another, why you can explain a joke perfectly and make it die on the table. The mechanics of humor involve something about social context, expectation, relationship, and a specific kind of surprise that is genuinely difficult to formalize. Which is probably why every attempt to write comedy by algorithm has produced things that are impressively, consistently not funny. Here's the quiet thread running through all of this. The hardest questions in science aren't the ones at the edge of observable reality, in deep space or inside quantum systems or at the boundaries of time. Those are hard, but they're hard in ways we expect. We understand why we don't know what dark matter is. The question is remote and the tools are limited. The hardest questions are the ones where we have been observing the phenomenon our entire lives, where we have every data point we could possibly want, where the thing happens in front of us and inside us constantly, and we still can't build a complete model. Because those questions are hard in a way that exposes something uncomfortable about the limits of scientific modeling itself. They require understanding not just mechanisms, but systems, not just neurons, but what neurons do when they're all doing it at once. Not just chemicals, but what chemical reactions mean when they're embedded in a body that has a history and a context and a really strong prior belief about whether it's been given medicine. Sleep is not a mechanism. It's what the whole system does when it decides it needs to do it. And modeling the whole system is hard. It may be, in the case of consciousness and its quirks, the hardest thing science has ever tried to do. The part I find genuinely clarifying, not just interesting, clarifying, is that this changes how you should think about confidence. We live in an information environment that is very good at projecting certainty. The explainer videos, the science communication, the documentaries with their ominous orchestral scores and authoritative narration. They are mostly telling you about the things we know, and there is a lot we know, genuinely a lot. Don't let anyone try to leverage "science doesn't know everything" into "therefore you shouldn't trust science." That's not the move. But there's a version of scientific confidence that flattens the edge, that implies the map is basically complete except for a few blank spots in the corners. And the blank spots in the middle, the ones that look like they should already be filled in, those are the ones worth paying attention to, because they're the ones that might change everything. The most important discoveries in the history of science didn't come from filling in a corner of the map. They came from someone looking at something completely ordinary and refusing to accept the first answer. Gravity wasn't discovered because someone found a new exotic phenomenon. It was discovered because someone sat with the extremely ordinary observation of falling things long enough to ask what was actually happening. Some of the most interesting research happening right now is sitting inside these mundane, unsolved questions. Sleep research is tangled up in Alzheimer's research in ways that could change medicine. Placebo research is quietly rewriting the mind-body assumption that Western medicine has run on for a century. Itch research is producing new ways to treat chronic conditions that have been misunderstood because they were misclassified. The answers to questions that have embarrassed science for centuries tend to be more interesting than the questions themselves implied, which means the next time someone gives you a flat, confident explanation for something you've always taken for granted, why you yawn, why you sleep, why something made you laugh, it might be worth sitting with the question a little longer than the answer suggests you need to. The things we've been nodding along to our whole lives are sometimes the things nobody actually understands yet, and that's not terrifying. That's where all the interesting stuff still is.